Thank you for introduction. Can you hear me? Should I use a microphone? Is it okay? Yeah. If I speak like this, maybe. Yeah. So thank you for inviting me to this wonderful workshop and with great view of Mount Fuji. I'm very glad. So last night, I think I told you that my talk was not gonna be related to Calabi-Yau, but I don't think that's exactly true, because probably you can identify some part of my talk which can be related to Calabi-Yau. I don't know how to, but you know probably. In any case, this is the only slide that word Calabi-Yau appears in my talk, and it appears there. Okay, so I'm going to talk about class algebras and three-dimensional integrable systems. So I would like to, first of all, remind you of what I mean by integrable systems. So what kind of systems I'm going to consider. So let's, first of all, look at two-dimensional case. So I'm going to explain to you briefly what I mean by two-dimensional lattice spin model. So two-dimensional lattice spin model is some model of some system, physical system, in which you have something called spin variables. And so let's say that we have spin variables. So each circle represents a spin variable. It can take discrete values 1 to up to n. And by lattice model, I mean these spin variables are located arranged according to a lattice. So I have drawn a lattice, 2x3 lattice, and it's supposed to be drawn on a torus. So I impose periodic boundary conditions. And these spin variables are located on the edges of a lattice. Do I have a? Yeah. Yeah. Yes, thank you. All right. So let's look at the neighborhood of a single crossing of two lines. It looks like this, and there are 4 spin variables surrounding a vertex, and they interact. And there's some kind of interaction energy. So let's say that spin variables take values I, j, k, l, respectively. And then there is a corresponding interaction energy associated to this local configuration of spin variables. Let's call it E, I, j, k, l. And the goal of, one of the goals of statistical mechanics is to compute a very special number, which is called the partition function, which is denoted by z. And what is that? It's the sum over all possible configurations of spin variables of exponential of minus the total energy divided by Boltzmann weight Kb times the temperature. So E is the total energy, so that's just the sum of all local energies. So sum over all vertices, and at each vertex you have this kind of interaction energy. And you would like to compute this. So this is just a definition, and you would like to compute it, and you want to get some kind of analytic answer. And it's usually a very hard problem. And most of the cases, you don't know how to do it. But for some special class of models, this is possible. And that special class of models are integrable models, which I'm going to explain now. So two-dimensional integrable lattice models, what do I mean by that? So in order to explain what I mean by this, let's introduce a n-dimensional vector space VA to the eighth line. So lattice has some lines, and to each line I introduce an n-dimensional vector space. And I introduce this operator RAB, which I call the R matrix, to the crossing of two lines, line A and line B. Okay, so so it's an endomorphism of VA tensor VB. And how do I define it? I simply define it by this giving matrix elements. So to this local configuration of spin variables located around the crossing of the 8th and bth line. And then there is this interaction energy and this something called Boltzmann weight, which appeared in the definition of the partition function. I just say that this operator has this matrix element, RABAIJKL, for this spin configuration. And that defines some n squared times n squared matrix. And that's this R matrix. Okay? And the important thing is that if this operator R satisfies the so-called Yang-Baxter equation, which takes this form, RRR equals RRR. Okay, how do I, so what I mean by this is that each equation, each side of the equation is actually an endomorphism of V1 tensor V2 tensor V3, and R12, for example, acts on V1 tensor V2 by this operator R. Okay, R23 acts on V2 tensor V3 by this operator R. Okay, so well, this is a key equation for integrable lattice models in 2D, and it also has this graphical representation. So the graphical representation of the Yang-Baxter equation looks like 3 lines crossing, intersecting on a plane, and then let's see that. So how do I read this? So well, you have line 1 and line 2 crossing here, and then I assign this R12, this factor here, to this intersection, and then you follow the direction of line, and then you see next line 1 and line 3 cross here. So to this intersection of line 1 and line 3, I assign a factor R13, and finally line 1 and line 2 cross, line 2 and line 3 cross, and then I have a factor of R23, that's this factor. So this picture represents the left-hand side of the Yang-Baxter equation. Okay. On the right-hand side can be obtained from the left-hand side by taking one of the lines, let's say this horizontal line, and pull it up, and this line passes the crossing of the other 2 lines, and until you obtain this configuration, new configuration of 3 lines. Okay? And the Yang-Baxter equation says that physically nothing really changes when you do this move. So that's the content of the Yang-Baxter equation. And then there's a famous argument, which I'm not going to review here, which says that if this R matrix, this operator you construct from the interaction energy satisfies this equation, then the model you're considering is integrable. There's a technical sense in which, by which I mean integrable. But yeah, I'm not going to really explain that. But the point is, if the model is integrable because this Yang-Baxter equation is satisfied, then it helps you compute the partition function. And this has been very powerful and influential. Examples of such models for which the R matrix satisfies the Yang-Baxter equation are the 8-vertex model, which is actually equivalent to one-dimensional XYZ spin chain quantum mechanical system, or two-dimensional Ising model is another example. Well, there are many more. But not only in this original context of statistical mechanics, the Yang-Baxter equation appears also in gauge theories, especially supersymmetric gauge theories and string theory, and of course, so quiver. Well, if you consider the quiver varieties and then the homology of quiver varieties, you can find the action of some Yangian, which is related to Yang-Baxter equation, and so on and so forth. So the list continues. So clearly, this is very, very interesting. But I have to stress that this is only about two-dimensional integrable lattice models. Okay? So the natural question is, what about three-dimensional models? Okay? So in 3D, there's something similar to Yang-Baxter equation, which is less known. So what about spin models on a 3D lattice? So how do you think about 3D lattice? You want to think about 3D lattice as created by intersecting planes. Okay, so here I have drawn 3 intersecting planes. Okay, and these arrow edges, oriented edges, are intersection of pairs of planes. Okay, so similar to the two-dimensional case, you can place spin variables on the edges of these black lines. Okay, and then let's say that they have ijk, lm, n, so these spin values, and then you can define this matrix element of some operator R. Now R, ABC, ABC are indices, labels for these planes. All right, R, ABC is some operator which is assigned to this intersection of three planes, plane A, plane B, and plane C. It's now an endomorphism of V, what I call VBC tensor VCA tensor VAB. For example, VAB is a vector space which you would like to assign to the intersection of plane A and plane B, okay, and so on. So you can define something similar to the two-dimensional case. So R matrix, so some people call it 3D R. And similar to the Yang-Baxter equation, there's a three-dimensional analog of the Yang-Baxter equation, which is called Zamolodchikov's tetrahedron equation. Now the equation contains, each side of the equation contains 4 R's. Okay, so this is the three-dimensional version of Yang-Baxter equation, and this implies integrability. And similar to the Yang-Baxter case, there's a graphical representation of this equation now, which now looks like 4 planes, intersecting planes, binding a, which bounds a tetrahedron. Okay, and you can take one of these 4 planes. Let's say this plane here. So there's a plane in the horizontal direction. Okay, you can pull it down, and until you obtain this new configuration of 4 planes. Okay.
So the vector spaces now of the tetrahedron equations are kind of 6. There are 6 of them.
Yes, that's right. So yeah, so yes, so this each side is an endomorphism of a tensor product of 6 vector spaces. So these vector spaces are assigned to pairs of planes, and so yeah, 4 choose 2, and you have 6 vector spaces. Okay, so so this is a tetrahedron equation, and you may or may not know this equation, and maybe this is your first time hearing about this equation. But let me tell you that tetrahedron equation actually has a relatively long history. So it was, as I said, it was introduced in 1980 by Zamolodchikov. And if you think about it, it was before the famous BPZ paper on 2D CFT. Okay, so it has a long history, but it's also fair to say that it's far less developed than Yang-Baxter equation. And actually, there's only, as far as I know, there's only one book which exists on this subject of tetrahedron equation, and which was written by my collaborator, Kuniba-san, and that appeared, published last year. Okay, so there's only one book. And so you may want to ask why there's not much development. Probably the reason is the equation is too difficult. All right, so Yang-Baxter equation is already difficult because it's an over-constraining system of equations, but tetrahedron equation is way more complicated than the Yang-Baxter equation. So coming up with solutions is very difficult. And so Zamolodchikov, in his original paper, wrote down first non-trivial solutions of the tetrahedron equation, and according to Baxter, by what appears to be an extraordinary feat of intuition. So it was really amazing that tetrahedron equation has solutions and it could be written down. Okay, but I would also like to say that the tetrahedron equation could be as rich as the Yang-Baxter equation, if not richer. So, and interesting solutions have actually been found by Zamolodchikov, Baxter, and all these people. And obviously, tetrahedron equation is important because from physics perspective, our space is 3-dimensional. So it makes sense to study 3-dimensional models. Okay? So from that physics perspective, it's also natural and very important to look at tetrahedron equation. Okay? So I hopefully I convinced you that studying tetrahedron equation makes sense. Okay, let me move on. So what I'm going to talk about is the following. We now seem to have a new approach to solving the tetrahedron equation, which uses something called cluster algebras. I think probably many of you know much more about cluster algebras than I do. So, but this approach was proposed by my work with my student Xiao-yue Sun, who should be sitting somewhere here. Yeah, he's sitting over there. So that was a paper we wrote already 2 years ago. So we constructed new solutions of the tetrahedron equation using something we call triangle, square, and butterfly quivers, and interpreted these solutions we obtained using three-dimensional gauge theories. More precisely, these solutions can be identified with the partition functions of three-dimensional gauge theory, n equals 2 supersymmetric gauge theories on squashed three-sphere. And this approach was further developed by Inoue-san, Kuniba-san, Terashima-san. They wrote 2 very nice papers last year. And they used and developed this approach and have reproduced known solutions of tetrahedron equations and moreover constructed new ones using the first 2 of these 3 quivers, triangle and square quivers. And then in the ongoing work, which we are finishing and which we hope to post on archive tomorrow, we took the last one, this butterfly quiver, and constructed 2 more solutions. Okay, so now I'm going to explain in this talk about this last item. Okay. And I would also like to add that even though I believe this is the first instance where cluster algebras were used to construct new solutions of the tetrahedron equation, there were some related work which appeared before. One particular one is Gavrilenko, Semeniakin, and Zenkevich from 2020. They reproduced something called classical L operator, three-dimensional L operator using cluster integrable systems. Okay, but yeah, why? So, and I would like to tell you why this is interesting. This new approach seems to be very powerful because many or probably most of known and interesting solutions of tetrahedron equation can be actually obtained from solutions we obtain using these cluster algebra approaches by certain special case, by certain special limits. Okay. And moreover, it seems that there are relations to the geometry of 3 manifolds using something called the 3D corresponds, which is related to 3D gauge theories, and also seems to be related to wall-crossing phenomena of BPS particles in 4D n equals 2 supersymmetric gauge theories, and also can be related to something called 4D Chern-Simons theory. Okay. So if, well, I will probably mention a little bit about these. Okay. So this is sort of like the introduction to what follows. So if there's any question, this is a good time to ask. Okay, so if not, I just move on. All right, so in order to explain the construction, I first of all have to introduce something called wiring diagrams. And to explain wiring diagrams, it's best to recall the definition of the symmetric group Sn, and that's generated by adjacent transpositions S1, S2 up to Sn-1, and they satisfy these familiar relations. Okay, so I think this is okay for everyone. But what we are interested in is an expression like this, SA1, SA2, Sak, so some product of some number of transpositions. Okay. So given such an expression, it can be, we want to represent it using a diagram called wiring diagram. So for example, as an example, let's take this expression of the product of these transpositions S1, S2, S3, S1, S2, S1. This can be represented nicely graphically using this wiring diagram. So here, I have 4 wires, so I'm considering this expression of transpositions for S4, so n is 4. And so when n is 4, I introduce 4 wires. Wires are these blue lines, blue curves. Okay? And then you read this expression from left to right. And the first transposition you encounter is S1. And then what I do is I interchange the first and second lines here. So there's a crossing of first and second line. And this crossing corresponds to S1. Okay? And the next transposition is S2, which should correspond to the interchange of the second and third wires, and which is this crossing, and so on and so forth. So I hope this correspondence between this expression and this diagram is clear enough. Is it okay? Yep. All right. And one remark is that we are going to identify isotopic wiring diagrams, which amounts to saying that I impose this second relation, but not the first and third one, all right, when we talk about wiring diagrams. Now, how are we going to use these wiring diagrams? Now, from wiring diagrams, we would like to construct quivers, all right? So that's what we are going to next. So given a wiring diagram, we want to assign a quiver. And the rule is the following. So what I'm going to do is I put vertices of quiver on the crossing and on chambers of wiring diagrams. So I think it's easier to just look at the example. So if you have two blue, so these blue curves are wires, and they cross here. At the crossing, I place a vertex, and I also place vertices on these white regions, which I call chambers. So I have 1, 2, 3, 4, 5 vertices in this neighborhood of crossing of two wires. And then around each crossing, I have vertices, and I connect them by arrows. And I now use 2 arrows, solid arrows, ordinary arrows, and dash arrows. Solid arrows, I give weight 1. Dash arrows I give weight 1/2. Okay. And then what I do is I just do this for each crossing of wires. And then for some pairs of arrows, there will be multiple. So for some pair of vertices, there will be multiple arrows connecting to those pairs. Okay. And then I want to combine them by adding up weights. But when I add these weights and combine these arrows into one arrow, I have to think about the orientation by giving different signs. Okay? So this is an example. So I have this wiring diagram, which is shown in blue. And then around each neighborhood of intersection of two wires, I have this kind of pattern. Okay? But then I combined and canceled some arrows according to the rule I explained. Okay. So the main point is, given the wiring diagram, I can construct this quiver. Okay. So this correspondence is going to be important.
So is there any meaning for the integers assigned to the vertex?
Oh, these integers are just labels for vertices. Yep. Because I'm going to refer to these vertices by numbers. Okay, and then given quivers, there are some operations you can apply to them, and which are called cluster transformations. Probably I don't really have to explain what these are, but one important thing is the mutation, mu k at vertex k. That's a transformation of a quiver, this directed graph, and produce to a new quiver. And the rule is the following. So if you see 3 vertices I, K, J, and connected by arrows like this, you have some arrows like this, and you apply a mutation at vertex K, what you first do is you add an arrow, additional arrow from I to j, and then reverse the orientation of all arrows connected to k, and then finally you combine or cancel arrows by considering weights correctly. So this is an example. If you start from this quiver and if you apply a mutation at the middle vertex, first thing you would do, the first step is to add these 4 arrows, and then second step is to reverse the orientation of arrows connected to the middle vertex, and then finally I combine these arrows. For example, this arrow and this arrow here, they cancel, and this arrow, dash arrow here, and this solid arrow, they don't exactly cancel, but it leaves a weight 1/2 dash arrow going from here to here. And anyway, so you, after the mutation, you obtain this quiver. Okay? And mutations are involutive, so that's, anyway, mutation. And there's another operation which is called an automorphism, which is just a relabeling of vertices. It's kind of trivial. Okay? So when I say a cluster transformation, it's a composition of any sequence of mutations and automorphisms. Okay. All right, so is this okay? Okay, so how am I going to use cluster transformations and construct tetrahedron equation solutions? So the point is, so there is some operation which is called the braid move, which I can apply to wiring diagram. So if you have a wiring y as a, b, c, and they make this pattern, then you can apply this braid move beta a, b, c, and you obtain this new pattern. Okay, you take the middle y b, you move this part up, and you get this one. And this induces a transformation of the associated quivers. So you have a quiver associated to this diagram, and you have another quiver associated to this diagram. And the claim is that these 2 quivers are related by a cluster transformation, which is a sequence of 4 mutations and relabeling. Okay? So if you start from this quiver, which is a quiver associated to this diagram, and then you apply mutation at vertex 4, you get this. Now you apply mutation at vertex 3, and vertex 5, vertex 8, and then finally you relabel a little bit, but this is kind of trivial, so I don't want to talk too much about relabeling, but then you obtain this quiver, which is exactly the quiver assigned to this this wiring diagram after you obtain after the braid move. Okay? So this braid move corresponds to a cluster transformation. Okay. Now, so which is actually, well, that is actually nice. And then I would like to switch gears a little bit, and I would like to remind you of a relation between quivers and gauge theories and how mutations are related to something called dualities, because this is going to give you a motivation to connect and kind of tell you how to connect all this to tetrahedron equation. Okay, so all right, so let me remind you how you assign how you construct a gauge theory with 4 supercharges when you are given the quiver. Okay, so recipe is really easy. So to each vertex I, you assign a gauge group, let's say SUN, and let's label it by the vertex label I. So you have SUNI to I vertex, and to each arrow you have some kind of matter, okay, matter field, which transforms in by fundamental representation of the respective gauge groups I and J. And in the quiver I also have half arrows, and if you don't like half arrows, because there's no half actually matter multiplied in these kind of theories. So if you don't like these half arrows, you can actually replace this rule for constructing this quiver by this rule, and then construction works. Okay, then you don't have any arrows, and actually the discussion that follows can also be applied for this version of quiver. But anyway, so given the quiver, you can construct gauge theory with 4 supersymmetries. So now, if I summarize what I have shown you, here we have the following corresponds. So given the wiring diagram, you can construct a quiver, and from a quiver you can construct a gauge theory. Okay? So whenever you see wiring diagram I showed you before, you should think of it as a gauge theory now via this correspondence. Now, why is this interesting? Because we know that in this kind of gauge theory, mutations of quiver, we know that they correspond to infrared dualities. And probably people may or may not have heard about infrared dualities, but what I mean by is the following. So if you have two theories which are called dual to each other, let's say T and T dual, if you have these two dual quantum field theories, and then if you calculate the same quantity, let's call it X, in the respective theories, the results match. Okay, so you get an equation like this. And that is actually nice. So let's apply what's known in quantum field theory to the current setup. So we know that the braid move you apply to braid wiring diagram. So you have this wiring diagram, you apply braid move, you get this wiring diagram. Okay? But we know that braid move corresponds to sequence of mutations of the associated quivers, and which correspond to infrared dualities of the associated theories. And if you take some quantity X, you calculate in the respective theories, then you get an equation. Okay. Now, what does that really mean? So let's take each side, well, let's take one side of the equation. So now you have this wiring diagram, which looks like this, and I have drawn for you the associated quiver. But if you look at this quiver, you notice that it can be decomposed into three simpler quivers. This one, and this one, each associated to two wires crossing, so simpler ones. So you have simpler theories. But from these simpler theories, you can combine them, and you can construct this more complicated theory. Now, if the quantity X you choose is nice enough, such as something called supersymmetric index, then the corresponding equation like this also decomposes according to this decomposition. So you get this kind of equation from this equation. But what is this equation? This equation is actually the Yang-Baxter equation, okay? Where the R matrix RAB is just this quantity X calculated for this calculated in this supersymmetric field theory associated to some quiver which is assigned to this diagram. Okay, so this is something called gauge YB correspondence. Masahito has pioneering work on this. So it's a very nice way to construct solutions of the Yang-Baxter equation.
Sorry.
Yep.
Where are the vector spaces?
Vector spaces are actually, well, they appear from some, so each of these theories have some parameters when you calculate this kind of quantity, and vector spaces are spaces of functions of such parameters. So spin variables are continuous for these models. But anyway, so I can construct solutions of the Yang-Baxter equation using this wiring diagram, the quivers, and mutations and dualities. But that's known. And so the question is, how do I lift this correspondence between gauge theories, quivers, and Yang-Baxter equation to tetrahedron equation? So I have to somehow lift everything to one layer higher. Okay. So the idea is the following. So instead of calculating some quantity X, let's look at the space of states, like Hilbert space of quantum mechanical state. Okay, so let's call it H. All right. Now I have a braid move which corresponds to dualities of the corresponding theories which are described by quivers assigned to these wiring diagrams. So on each theory you can consider the space of states. And then duality, by duality, what do I mean? Well, by duality, duality doesn't tell you that Hilbert space of states in this theory and the Hilbert space of states in the dual theory are equal. duality just tells you that they are isomorphic. So which means that duality gives you some kind of operator R, which I call RABC, which gives you an isomorphism like this. Okay? But now there's something very interesting. If you look at this particular wiring diagram, this is a wiring diagram with 4 wires, and this actually corresponds to a reduced expression of the longest element of the vial group of A3. And then there's actually a sequence of braid moves you can apply. Actually, that consists of 8 braid moves, 4 braid moves, and 4 inverse braid moves. And then this diagram comes back to itself. Then what does this mean? This means that if you look at the corresponding isomorphisms of the Hilbert spaces with the corresponding quantum field theories, this fact means that this combination of these isomorphisms is an endomorphism of the Hilbert space of the quantum field theory, which is assigned to this wiring diagram. Okay? But now, if you look at this, it looks a lot like the tetrahedron equation already. All right? If this operator, which you can construct from this loop of braid moves, is for some reason is equal to identity operator acting on this Hilbert space, then this equation is actually the tetrahedron equation. Okay? So the question is whether this is true for, say, 4-dimensional supersymmetric gauge theory associated to this wiring diagram. So that's a question you can ask, and I don't know the answer. But I know that something like this happens for simpler theory. Okay? And you can actually construct you can use something called the theory of quantum cluster varieties developed by Fock and Goncharov to construct simpler quantum mechanical systems, one-dimensional systems in which this equation holds. Okay? So this is the main idea. This was the main idea of my work with Xiao-yue. And this is how you construct a solution of the tetrahedron equation. Okay. So I hope I haven't lost people. And yeah, it's okay. So that's the main idea. I hope it was understandable. And I have spent, so I have like 20 more minutes, or what? Yeah, 22?
More than 22.
Okay, so all right, so I have a lot of slides, but let me try. So to construct the such solution of the tetrahedron equation, in our work we use quantum class algebras. So I have to tell you what that thing is. So one way to define it is the following. So first of all, given a quiver can be encoded in an antisymmetric matrix called the exchange matrix of that quiver. Okay, so it's very simple. So exchange matrix B has elements B, I, J. I and J are valued in this set of vertices I. And Bij is either equal to 0 or 1 or 1/2. In our case, Bij is equal to 0 if there's no arrow between vertex I and vertex J. It's equal to 1 if there's a solid arrow going from I to J. And 1/2 is there's a dash arrow from I to J. Okay?
So more or less it's like adjacency matrix.
Yeah, it's the same thing.
Okay.
Yeah, right. But it could be 1/2.
Oh.
Yeah. Okay, and then mutation can be written in terms of some formula for transformation of this matrix to B to a new matrix B prime. Okay, and it's just there's just some formula. I can't remember this, but you don't have to remember it. But now, what's quantum class algebras? I'm going to use one particular version of quantum class algebras, which are generated by something called the quantum Y variables. So Y variables are some non-commutative variables. There is one Y variable to each vertex of a quiver. So, and they satisfy this non-commutative relation. Yi assigned to vertex I and Yj assigned to vertex J satisfy this relation. So I'm going to use these non-commutative variables. Now, important point is that given a mutation mu k, applied at vertex k of a quiver B, which transforms a quiver B to B prime, this mutation actually induces an isomorphism of this curly YB, which is a skew field. So it's a rational expression of the quantum Y variables, but it goes in the backward direction from B prime to B. And this is some kind of pullback by mu k star. And it can be written in two different ways, but the result is the same. Okay, so there's a choice of sign you can make, but choice of sign in the end doesn't matter. The result is going to be the same. So first one, so it's a decomposition. Well, this mu k star can be decomposed into the adjoint action by the multiplication by psi q. Psi q is a quantum dilogarithm. And then there's some additional piece tau k, okay, here. That's just, that acts like this. Okay. But anyway, so there's some formula for mu k star. And it gives you an isomorphism between the quantum cluster algebras assigned to quivers related by mutation. So the idea is I had a sequence of mutations, and I would like to consider the corresponding isomorphisms. Okay, so let's try to do that. So let's recall what braid move did. So you had a wiring diagram like this. I applied braid move, and I get a new wiring diagram, and correspondingly, the quiver was transformed to a new quiver. Okay, and then we have seen that this satisfies well, there's a loop of braid moves, and that actually, so this beta ABC satisfies this equation. If you multiply these betas and beta inverses and apply that to this wiring diagram, then this wiring diagram is invariant. Okay, and the corresponding quivers are invariant. But if you look at if you just calculate what these braid moves do to Y variables, quantum Y variables, you find that these braid moves, this composition of braid moves, also leave the Y variables invariant. And that's actually very, very non-trivial. I thought maybe in many cases when the quiver remains invariant under certain cluster transformation, then the corresponding Y variables would be probably invariant, but that's usually not the case. But it's the case here. Okay? So which means that there's this composition of braid moves, composition of cluster transformations, mutations, and relabelings. If you take the corresponding action of that on the pullback of that on Y variables remains invariant. Okay, which is very nice because I wanted something like that this is equal to identity. That's going to be the tetrahedron equation. So indeed, I get a solution of the tetrahedron equation by just setting R hat ABC to be this beta ABC pullback. So this acts on Y variables. Then this operator satisfies the tetrahedron equation. And you may think that, well, we obtained a solution. But this is actually not the solution we want. Okay? So there is another step to construct a solution which we really want. Because this is a tetrahedron equation, and each side of the tetrahedron equation acts on this quantum cluster algebra assigned to certain quiver and wiring diagram, and gives you some element of quantum cluster algebra assigned to another quiver. Okay? But this kind of thing is not what I wanted to get. I wanted to get some solution of the tetrahedron equation which acts on the Hilbert space of states. Okay? So what does it mean? So what I want to do now is that I would like to consider those Y variables, quantum Y variables, as operators acting on these Hilbert spaces. Okay? And these R hats are some unitary operators which implement this kind of isomorphism. Namely, I want R hat acting on yi and want to express this as a conjugation action by some operator R. Okay, is this okay? So R is a map from space of states to another space of states, and R hat is a map from the operators acting on the Hilbert space to operators acting on another Hilbert space. Okay? And I want to obtain such R instead of R hat. And this R is going to be a nicer object.
So R hat acting on Y variables.
Y variables. But R is going to act on some vector spaces.
I see.
Okay? So that's what you want, actually. Right, so how do we do that? So let's recall what the exact form of beta 1, 2, 3. I told you that it's a product of 4 mutations, and then there are some relabelings. But anyway, so this is a formula. And also remember that this action of mutation on Y variables, these quantum non-commutative variables, can be written like this. There's a choice of sign, epsilon. It can be either plus or minus, but the result is the same for either choice of sign. But if you plug this definition in here, and then you just calculate this what this R hat is in terms of these adjoint action by psi of Y and tau, then it looks like this. I just plugged that in, formula in. But then you can actually move these taus all the way to the right, and you can write everything in this form. Adjoint of some operator, adjoint action by some operator times 4 taus and some relabeling. The problem is that you have this piece, okay, which is not the adjoint, usually not the adjoint action of something. If you can write this piece as adjoint action by some operator P1, 2, 3, then the entire thing, R hat, can be written as adjoint of something, R1, 2, 3, where R1, 2, 3 is this something which sits in here, and this P1, 2, 3. Okay? So when does this happen? How do we do this? Well, there are 2 ways. One way is the way which was pursued by Fock and Goncharov. It realizes this quantum Y algebra by position and momentum operators, and well, this requires actually doubling the number of quantum dialogues, and then this was a route I took with my in the paper with my students. But then Inoue, Kuniba, Terashima wrote very nice papers which told us that how to do this using something called Q-vial realization, and that's the direction we are going in our new work. So I would like to explain this.
Sorry, this
Yep.
P1 to 3 here.
Yep.
Is it similar to the permutation operators?
Yeah, permutation appears. Yes. Yes. Yeah.
But it's a combination.
Yeah, it's more complicated. I will show you a formula. All right. So now, what's Q-vial realization? So remember that there was this wiring diagram, this local picture, and then there's a quiver, and there were vertices, and to each vertex you assign a quantum Y variable. But now the idea is I introduce to each crossing of Ys, to alpha crossing of Ys, I assign canonical variables U alpha and W alpha. They satisfy this Heisenberg relation, H bar. And I set Q equals e to the H bar. Okay? And then to each of these vertices, I assign some combinations of U and W and some parameters. These are all commuting parameters in this way. Okay? Then if you look at if you calculate the commutation relations of these variables, the exponentials of these variables actually do satisfy the correct commutation relations for quantum Y variables. Okay? And well, I don't really have time to go into detail and explain how this works, but it's really simple. So in this example for 3 Ys crossing, I have 10 vertices in the associated quiver. I have corresponding 10 Y variables, but each Y variable can be written as exponential of some linear combination of these U's and W's assigned to introduced to these three crossings. Okay. So I can realize these y variables using these canonical variables. And why do I want to do that? Well, it turns out that if you do that, and here's a nice little theorem. So if I realize these y variables using those canonical variables, and then there exists such the operator P1 to 3, such that the relation we wanted to get is true. Okay, and this is true for so there are choice of signs for each mutation. All right, and then so those signs are epsilon 1, epsilon 2, epsilon 3, epsilon 4. We could choose signs for each epsilon, but there exists such an operator P1 to 3 for which this equation is true if and only if these signs are either minus, minus, plus, plus, or minus, plus, minus, plus. So this is just a brute force calculation. Okay? So now the point is that if there is such an operator P1 to 3, then you can actually go back to several slides back, and then you can actually see that you can construct this R1 to 3 operator, and you can show by rather easily that this R1 to 3 solves the tetrahedron equation. Okay? And here I give you an explicit formula for the solution of the tetrahedron equation constructed in this manner. Okay? And P1 to 3 is given by this. As you say, well, there's a permutation operator here, but there are some shift operators multiplying permutation operator.
And all those lambdas?
Lambdas are some C numbers. Yeah, well, linear combinations of the parameters, C number parameters I introduced before. Okay. Now, so what's good about this solution is that this solution is written as in terms of elements of algebra. And then there's a choice of representations. All right, and you can choose different representations, and you get different solutions of the tetrahedron equation. So in our work, we mainly consider two representations: coordinate representation or momentum representation. Or each representation has a basis vectors labeled by 3 integers n1, n2, n3. In the coordinate representation, UK, the coordinate variable, is diagonal. In momentum representation, W, well, this has to be W. Is this W? Yeah. W is in the momentum representation, WK is diagonal. Okay. And in each case, you can actually calculate the matrix element of this operator, and you reproduce known solutions. And that's kind of amazing that, so for example, this solution you obtain from coordinate representation is a solution obtained by Kapranov and Vovotsky in 1994, but they obtained this from a very different point of view. Okay? And moreover, our solution has more parameters. If you set all of those parameters to 0, you reproduce this solution. So probably this is one of the most well-known solutions of tetrahedron equation. Okay.
Are the parameters of difference form, or
So,
could one massage it into the difference form of this?
difference form.
Yeah. I mean, it depends on A1 to A whatever.
Yeah, this operator depends on all of these parameters.
Exactly. But
Yeah.
could you?
Oh, you mean these parameters appear in some linear combination, but not necessarily like difference. Yeah.
But is it possible?
We haven't thought about that question.
Okay.
Okay, and there's one more thing. So there's something called modular double version, where quantum dialogues are replaced by something called non-compact quantum dialogues, and then we can also easily write down solution corresponding to that modular double setup, and we obtain a generalization of a solution, which was obtained by these people, Bajenov, Magzev, and Sergeyev. So they obtained this solution from the consideration of some quantum geometry of 3 manifolds. Okay, So in view of time, I would like to, I have like 5 minutes. So yeah, probably let me also tell you that in, there is also a brain construction of a solution of tetrahedron equation. So I explained that I could evaluate the R matrix in coordinate representation and momentum representation, where n1, n2, n3 run over all integers. But there's a representation which by Fock space, where n1, n2, n3 only run over non-negative integers. And so the corresponding solution, I conjecture in this paper that it arises from this brain construction in M theory. So the idea, roughly speaking, is I told you that three-dimensional lattice, you can think of it as intersecting planes, right? And I literally think of those intersecting planes as brains in 11-dimensional space-time. And then there were spin variables on the edges of the three-dimensional lattice so constructed. And those I conjecture that they actually, in this case, spin variables are non-negative integers. And I conjecture that they are just counting the numbers of M2 brains stretched between the intersecting M5 brains. Okay. And there's, well, but this may seem like it's all vague, but you can actually apply a chain of dualities to go from this setup, brain setup, to another brain setup. And in another brain setup, that's known to be related to something called four-dimensional Chang-Simons theory studied by Masahito and Kevin Costello and Witten. And yeah, so this construction is actually related to the trigonometric setup of 4D Chang-Simons theory. And also this solution is known to be related to the solution of the Yang-Baxter equation, trigonometric Yang-Baxter solution of the Yang-Baxter equation. So everything matches very nicely. Okay, and finally, let me briefly explain to you that you should also expect that there are relations to 3D gauge theories, three manifolds, and wall crossing phenomena. The reason being the following. So in the paper I wrote with my students, we used another representation called Fock-Goncharov representation. And then we obtained a solution of the tetrahedron equation. And that solution actually actually coincides with there's an integral expression of the partition function of a three-dimensional n equals 2 supersymmetric gauge theory on the something called squash 3 sphere. So it's a deformation of 3 sphere, and there's a deformation parameter b. Okay, and so you can write down a certain three-dimensional gauge theory, and there's a localization formula, something called the localization formula. That's an integral of some complicated function, and which depends on parameter b and other parameters. And if you look at that integration formula and look at the solution you obtain from doing this Fock-Goncharov representation thingy, then you see that they're equal. Okay, and furthermore, the kind of theory you obtain, this 3D theory, that's exactly the kind of theory that arises from compactification of 6-dimensional, something called Tukholm-Zier theory, on a 3-manifold.
Excuse me, what's different that manifold from S3? It looks diffeomorphic to S3.
But the answer depends on B. The partition function depends on B.
So which kind of structure you use, the metrics or something?
Yeah, it depends on metric. Yes.
It depends on metric.
It depends on metric.
Transverse holomorphic foliation.
Okay. So there's a vast field called the 3D corresponds, which studies this compactification of 6-dimensional theory on 3-manifold, and so geometry of 3-manifold is reflected in the 3-dimensional theory you obtain by this kind of compactification. And this 3-dimensional theory, which is related to tetrahedron equation, is exactly the kind of theory you can obtain from this kind of compactification. Okay, and finally, in this work, this loop of braid moves or loop of mutations, which was important, but that kind of loop of mutations of quiver appears very naturally in the setup of BPS wall crossing, okay, of 4D n equals 2 supersymmetric gauge theories. So I expect that this kind of three-dimensional theory appears as a domain wall in four-dimensional theory. Okay, and when you cross the domain wall, there's the quiver corresponding to describing BPS particles get mutated, and you go around like domain walls and come back to the same quiver. So I expect that this solution actually arises from a domain wall in 4D theory. So the natural question would be, does the tetrahedron equation actually hold at the level of domain walls without calculating its S3 partition function? So that's, this is still very vague, but that's the direction, kind of, these are the directions I would like to go. Okay. Okay, so let me wrap up. So here's the conclusion. So the one of the main messages obviously is that the tetrahedron equation is a 3D analog of Yang-Baxter equation. I would like to advertise this fact. It's important, but needs more study. Okay? And then, so it's interesting to construct new solutions, and new solutions can be constructed using quantum cluster algebras via loop of mutations on quivers assigned to wiring diagrams. And furthermore, solutions can also appear from some brane systems, AM theory, and 3D gauge theories. So now we have different approaches. One obvious question is how these approaches are related, because you actually can obtain same solution. And then, as I said, it seems like there are connections to three-manifold geometry and wall crossing. What exactly are these connections? And finally, I think as a physicist, I would like to come back to physics. So how are all of these be related or useful for understanding of three-dimensional statistical mechanical systems? So that would be the final goal. Okay. So that's all I wanted to say today. Thank you. So the question was, what's the role of the weight 1/2 arrows? Right? So actually, everything I set up to the point, up to this point works for. So let me go back. So I said something like, yes. So here I said if you don't like half arrows, you could as well use this assignment of quiver. And everything goes through until the point I realize these y variables using Q-vial algebras. So everything works until this point. And if you use Fock-Goncharov way of realizing this y variables using momentum position variables, it works for both quivers. But if you want to realize y variables by Q-vial algebras, so these canonical variables assigned to crossing, then it turns out that you have to use this version of quiver. So I don't have any more intuitive or a deeper understanding of this fact, but it's just something you find by doing this. So one version can be applied, can be used for this Q-vial realization, but not the other one.
And second question. So do you have any principles behind to find the solution of the power sequencing sequence?
Question was what? So this one, right? So basically, why this is true? Why? Yeah.
The solution is very complicated.
Yes. It's a very good question. So I don't think we have really a good understanding of why when we take this. So there is a degree of freedom of choosing 4 signs, and only for these 2 choices, then this additional piece which I didn't like can be written as a joint action by some operator. We don't really have a good understanding of why that's true. This is more like a brute force calculation by Mathematica. So probably these signs can have some geometric meaning in 3 manifold, maybe.
So there was a question of whether this has is to do with Calabi-Yau geometry. And then one thing which occurred to me is that first of all, in this discussion, it's very critical that the y variables come back, right? So after
yes.
the tetrahedron equation. And the one context of why y variable appears is that related to Mauritius work, but there is a GLM SM description of the Calabi-Yau modular space.
Yes.
And there is a cluster chart because there is a cluster variables arise from two common two series.
Yes.
And then so now if you formulate in that context, if you try to have the situation where you come back to the same coordinate, that might happen when there is a non-trivial monodromy on the Calabi-Yau modular space when you go through, and then there are two different paths and leading to the same. And maybe it doesn't give rise to not exactly the tetrahedron equation, but you get some equation coming from non-trivial monodromy. And I wonder if you can realize the non-trivial, the fact that and then you can try to quantize it.
Yes, I see.
To index. And I wonder if you can, to simply put, I wonder if they can use the monodromy on the Calabi-Yau to realize the invariance of the quantum y variable, and then extract generalizing the tetrahedron equation. It's just
I see. I think that's a really interesting suggestion. Suddenly that's very interesting, and we haven't looked at that direction at all. So first step would be to see whether this cluster algebra can be what target or what GLSM corresponds to this cluster algebra, this particular one. Another comment I would like to make is that sometimes the quiver comes back, but y variables don't come back after a loop of mutations. In that case, probably you would have to go further, higher levels. And so you have Yang-Baxter equation, tetrahedron equation, but in general, there's something called n-simplex equation. When n equals 2, you have Yang-Baxter. N equals 3, you get tetrahedron equation, but you have higher dimensional ones. So when the y variables don't come back, probably you would have to go one or more levels higher.
Yeah, so in that context, one natural question is if I'm going to the infinite categories, I wonder if you can formulate like an infinite simplex equation in infinite categories.
Yeah.
I wonder if some mathematician.
Yeah, obviously that was not the question he asked me. All right. So I hope someone can answer those questions. Thank you.